Okay, I'm going to go ahead and start breaking this down into its individual components so that we can kind of formalize the coding on this. Let me talk about this setup first. Here you can see we have a taro sensor that's hooked up to this breadboard right here. And this is exactly the same way it's hooked up in the field. There's a yellow wire that goes from the sensor bus all the way to that pin right there. And that's defined in code. So you can have multiple sensors basically hooked up to the microcontroller. What's important is that this little signal wire that comes off of each sensor basically goes to the same pin that's defined in code. Okay, let's not worry about that right now. What I wanted to do first was talk about the solenoids. And the relays and how we signal them. So this is basically the relay board. These are the wires, and I use the same colors that are currently installed in the field and the same pins. So there's a green wire in the field, a white wire, and then there's two black ones. There's a top black one and a bottom black one. The bottom black one, in this case, I basically have it as a gray wire here, okay? And it's loose for a reason. Okay, and I'll talk about that shortly. The bottom line is that those four pins are defined in code right here, what those wires are connected to, and we just define them as constants. And we're going to do that in our code right at the beginning because that will allow us to change things very quickly. We can change it here, and it should change anywhere we call valve 1, valve 2, valve 3, and valve 4. So we're going to want to do that at the top of our code. In the setup, we're basically defining those pins right there, which we're referring to as their constants as output pins, which means that they're basically going to be sending a signal out to the relay. And then we set them all to high, which means we've got 5 volts on each one of those pins. And the logic of this relay board is whenever it receives a signal from those pins as high, the relay switch is going to remain open. When we ground it, or when we set the signal right here to low, it's going to close those relays. And when those relays close, then current can flow to whatever we want to control on this thing. Okay, so right off the bat in my setup block, I'm going to make sure that they're all set to high. Okay, now we're moving on to our loop. This is the part of the code that's just going to basically run forever until we cut current or cut power to the microcontroller. So anyway, what this says here is what we're going to do right off the bat is we're going to basically set valve 1 or the pin associated with valve 1 to low, which means it's not going to have a 5-volt signal on it. We're going to wait a half a second. And then we're going to echo something to the screen that basically says valve 1 now has current because we set that pin to low, which caused the relay to basically register that it should close the switch and engage the solenoid, which will turn the irrigation on. We're going to cycle through all of these basically and just, turn 2 on for 500 milliseconds, turn 3 on for 500 milliseconds, and then do the same one with valve 4. On valve 4, I should mention that what I've done is I've hooked up these LEDs right here. So that's kind of like an indicator that there's actually current that's going to the solenoid. I don't have a solenoid here, so I'm using the LEDs right here as a surrogate for that. And they're powered the same way the solenoids are powered, which is basically off of a 12-volt wall wart. So it's the same voltage that we're currently using out in the field. So this perfectly mimics what we have installed at Biosphere. So when that one comes on over here, when valve 4 is triggered low, we're going to wait 2.5 seconds, and I'm going to echo a little message saying that, hey, the LEDs are on basically as a surrogate for flow. And then we're going to turn the 4 valves high, which is basically going to cause the relay switch to open. And when the relay switch opens, there's no more current going to those solenoids. And they're all basically going to be open, and we're going to, by open, I mean the switch will be open, which means that we don't have any current. And as a result, the message is that there's no more current and that the flow is basically going to be off. And you'll see that when we hit that fourth one, the LEDs are basically going to shut down. Okay, so let's go ahead and turn this on and see how it works. Okay, there you have it. So this is basically what the code is doing. Right now it's setting all those pins to low to turn things on. When it reaches the fourth one, it's going to turn on those LEDs to basically say, hey, stuff is flowing through the switch. This makes sense. All the pins are currently low. Now all the pins are being turned high. Stuff is getting turned off. Now it's all being turned back on again. So it's just one piece of the puzzle. And just the last thing I wanted to mention, don't forget that we do have these little messages that we're sending to a serial terminal, and there it is. So you can basically track what's happening on the screen, the logic of what's happening on the screen at the same time that it's actually happening via the relay. I can't get it all in there at the same time, but you get the general idea. Okay, and one more thing I wanted to talk about, and that has to do with, you'll see valve 4 here is defined as pin 13. That's a problem. I kept it as pin 13 because that's the way things are currently wired in the field. But pin 13 is also associated with that little LED right there. And whenever we upload code, that little LED is going to flash, and it's going to cause that switch to basically rattle, because it's tied to the same pin. So that can damage the relay if we do that repeatedly over time. I'm gonna demo that just once. So I'm gonna come over here, and I'm gonna upload the code. You hear that rattle? That's not good. We don't wanna do that. So anytime you upload code, for now, just remove this little gray pin, which is loosely attached. And after the code has been uploaded, you can very easily reinsert it. And it'll work normally. But the reason I kept that as pin 13 is because I'm trying to mimic exactly what we have installed in the field. We can change that later. Whatever we change, we need to document so that when we go into the field, we change it in the field too. And some pins are better than others for doing this kind of signaling. So we're gonna have to go over the pinout diagram for that microcontroller, perhaps pick a better pin for doing that. And in closing, let me just mention a couple more things about this setup. So what we've got here is the cigar box, and what I did was I included, let's see, there's a screwdriver so you can work with the terminals on the feathered terminal. There's an Ethernet cable, there's a multimeter, and there's a bunch of jumpers. So those will come in handy later on. You should have wire strippers in your Biosciences eSlab. I'll see if I can dig up an extra pair and throw those in there as well. But that's just so you have everything located in one place. And I'll also include this, this cable for being able to communicate with the microcontroller. So in closing, this is just part one of what'll probably be 6 parts that we need to put together and document. And what we're gonna do is break that code that Jahir has into a bunch of little pieces. And we can document each one of those pieces of code the same way we've done here, maybe with a little short video. And then we're gonna piece all those little modules together into one big piece of code that does exactly what we want. But it's kind of hard to take what we currently have and really understand it, at least for somebody who doesn't know how to read it. So let's break it up into a tiny bunch of little pieces that we can put together like Legos to do exactly what we want down the road. So this is the first one. This is the first module, I guess, or first part.